Hi everyone. Today we're going to study Warshall's algorithm. The concept of the interior vertices of a path is used in Warshall's algorithm. Suppose that R is a relation on a set with n elements. Let v sub 1, v sub 2, up to v sub n be an arbitrary listing of these n elements. Examples: the interior vertices of a path A, C, D, F, G, H, B, and J in a directed graph are C, D, F, G, H, and B. The interior vertices of A, C, D, A, F, B are C, D, A, and F. Note that the first vertex in the path is not an interior vertex unless it is visited again by the path, except as the last vertex. Similarly, the last vertex in the path is not an interior vertex unless it was visited previously by the path, except as the first vertex. Warshall's algorithm is based on the construction of a sequence of 0-1 matrices. These matrices are W sub 0, W sub 1, up to W sub n, where W sub 0 equals capital M sub R is the 0-1 matrix of this relation. And W sub k is equal to the matrix with elements small w sub ij raised to k, where the element w sub ij that is raised to k equals 1. If there is a path from v sub I to v sub j such that all the interior vertices of this path are in the set v sub 1, v sub 2 up to v sub k, the first k vertices in the list, and is 0 otherwise. The first and last vertices in the path may be outside the set of the first k vertices in the list. Note that W sub n equals M sub R asterisk because the ijth entry of capital M sub R asterisk is 1. If and only if there is a path from V sub 1 to V sub j with all interior vertices in the set V sub 1, V sub 2 up to V sub n. But these are the only vertices in the directed graph. Let us see this example. Let the relation R equals the ordered pairs 1, 4, 2, 1, 2, 3, 3, 1, 3, 4, 4, 3 on the set capital A with elements 1, 2, 3, and 4. Find the matrices W sub 0, W sub 1, W sub 2, W sub 3, and W sub 4. We have some notes here. Set A has 4 elements, so 4 by 4 matrix is required. Another note, W sub 4 is the transitive closure of R. Now let's begin finding W sub 0. This is a 4 by 4 matrix. Let us assign values or labels to the rows and columns respectively. For the rows, we write the 1, 2, 3, and 4. For the columns, same numbered from 1 up to 4. Next, in the ordered pair, take note that X value corresponds to row, while Y value to column. We write 1 if the ordered pair exists or 0 if not. Now let's begin with the first ordered pair 1, 4. Let us consider here the first row and we write 0, 0, 0, 1. The number 1 here corresponds to that 1, 4 ordered pair. And we have 0, 0, 0 in the absence of the pairs 1, 1, 1, 2, and 1, 3. Next are the ordered pairs 2, 1 and 2, 3 respectively. Look at the second row. We write here now 1, 0, 1, 0. The number 1 here corresponds to 2, 1. The number 1 here corresponds to 2, 3. And we write 0 for those missing ordered pairs. Next, let us consider the ordered pairs 3, 1 and 3, 4. Look at the row number 3. So we write here 1, 0, 0, 1. The number 1 here corresponds to 3, 1. The number 1 here corresponds to 3, 4. Next, the last ordered pair 4, 3. In the last row or the fourth row, we write 0, 0, 1, 0. The number 1 here corresponds to the ordered pair 4, 3. Now, W sub 0 matrix is secured. It is now here. Let's proceed writing the matrix W sub 1. The C sub 1 here means column 1. We're going to write all the elements of column 1. Considering our W sub 0, this is the column 1. We can see that there are two seats here with numbered 1. When we write the elements of C sub 1, these two number 1s here corresponds to the numbers 2 and 3 respectively. Therefore, the elements of C sub 1 are 2 and 3. Now let's consider the R sub 1, meaning row 1 of W sub 0. We're going to write all the elements of R sub 1. In the row 1, there is number 1 here that appears only once. Writing the element of R sub 1, this number 1 here corresponds to number 4. Therefore, the element of R sub 1 equals 4. Once we write the C sub 1 and R sub 1 elements, we will do now the Cartesian product of C sub 1 by R sub 1. And the elements are the ordered pairs 2, 4 and 3, 4. These two ordered pairs must be added to the relation R. This is our R here, to become R sub 1. Later, we will form the W sub 1, the matrix itself. Just to show, we can write R sub 1 equals the relation R, which is the given, plus the two new ordered pairs here. Let us identify the seats of these two ordered pairs. And these are the seats. We can see that one is 0, that corresponds to 2, 4. Other is 1, that corresponds to 3, 4. The number 1 here means that 3, 4 already exist in the relation R, while this 2, 4 is a new ordered pair to be added. In writing the W sub 1, we will just simply copy this matrix W sub 0. But because of this 0 that corresponds to 2, 4, and this 2, 4 now exists, we're going to change this 0 into 1. So W sub 1 becomes like this. The 0 here now becomes 1. We are now able to write the W sub 1. Let us now write W sub 2. Let us now consider the C sub 2, meaning the elements of column 2. In doing this, we're going to consider the W sub 1 matrix. So this is the column 2. We can see that all the elements are zeros, meaning the elements for C sub 2 is none, meaning C2 is an empty set. Let us consider the R sub 2. For this R sub 2, this is row 2. We can see that there are 3 number 1 here, and the 3 number 1 correspond to the elements 1, 3, and 4. But since the C sub 2 is empty, there is no Cartesian product here. In this case, we conclude that W sub 1 is equal to W sub 2. Therefore, the W sub 2 is the same with W sub 1. Then let us write now the W sub 3. Let us consider the C sub 3, meaning we will write the elements of the set of the column C sub 3. With regard to our W sub 2, this is our column 3. There are 2 number 1 here. This 2 number 1 correspond to the elements 2 and 4. Now, let us write the R sub 3, the elements of row 3. This is our row 3 here. There are 2 number 1. The elements corresponding to this number 1 in row number 3 are 1 and 4 respectively. Then we will now write the Cartesian product C sub 3 times R sub 3. The elements are 2, 1, 2, 4, 4, 1, and 4, 4. These new ordered pairs must be added to the relation R sub 1 to become R sub 3. Take note that we skip the R sub 2 because R sub 2 is the same with R sub 1. We will write here the subscript 3 to conform with our W sub 3. Considering the ordered pairs of this Cartesian product, let us identify the seats of these pairs in our matrix. These are now the corresponding seats of the ordered pairs. The 1 and 1 corresponds to 2, 1 and 2, 4. The number 1 here means the 2, 1 and 2, 4 are already existing in R sub 1. Now for the 0 and 0, it corresponds to 4, 1 and 4, 4. In writing our W sub 3, we will simply copy the W sub 2, except that for the 0 and 0 here that we identified, we're going to change it by 1. So it becomes like this. Take note, the 0 here becomes 1. Also, the 0 here becomes 1. And the remaining entries are same. Now let us write W sub 4. Let us first consider the elements of column 4 with respect to W sub 3. This is the column 4. There are 4 number 1 in here. So the elements are 1, 2, 3, and 4. Let us consider now the elements of row 4 with regard to our W sub 3. This is our row 4. There are 3 number 1 here. The number 1 are corresponding to the elements 1, 3, and 4. Next step, we will do the Cartesian product C sub 4 times R sub 4. The elements are in here. These new ordered pairs must be added to the relation R sub 3 to become R sub 4, and then we will form the W sub 4. Just to show, we will write that R sub 4 is equal to the R sub 3 plus the new ordered pairs from this Cartesian product. Let us now identify the seats of the new ordered pairs in the matrix W sub 3. And these are the seats of its new ordered pairs. We can see that some of them have 0, some of them have 1. So when we write the W sub 4, we're going to copy the elements of matrix W sub 3, except that those identified seats with zeros we will change by 1. W sub 4 becomes like this. Look at the first row. We have now 1, 0, 1, 1. Second row, 1, 0, 1, 1. Third row, 1, 0, 1, 1. Fourth row, 1, 0, 1, 1. This W sub 4 is the transitive closure of R. So we have now the matrices W sub 0, W sub 1, W sub 2, W sub 3, and W sub 4.